Hello everyone, so in this video I'd like to talk through 4.5, which is a summary of curve sketching. The good news is that there's not too much new here. It's basically a summary of things we've already seen. And the idea is, okay, what are the geometric properties of curves that we can understand using calculus, and what can we compute to either help us sketch the curve or to help us understand why the curve is sketched the way it is. So the structure is basically we're going to go through a couple of properties we've already seen, and then we're going to see how to use them all together to sketch a curve. And yeah, that's about it. So let's get started. So what is going to help us sketch y equals f of x? Suppose we're given a formula and we want to understand what the graph looks like. Okay, there are a bunch of things that we can look for. So maybe the first is the domain, which is the values of x for which the function f of x is defined. And of course, we are only going to sketch the graph in this region. So we have to look at where the formula makes sense, and then we can only sketch it for the x where it makes sense. Right, and typically we're looking at, if f is a composition of more complicated stuff or simpler stuff, we're looking at when the individual pieces make sense, and then we need all of them to make sense for our formula to be okay. So for instance, ln x has domain 0 to infinity, 1 over x has domain x not equal to 0. Yeah, and for instance, you want to get rid of square roots, you want to make sure square roots of you only take square roots of positive numbers, and so on. Okay, the next thing is our intercept. So the y-intercept is where the graph crosses the y-axis, which is when x equals 0. So the y-intercept is going to be y equals f of 0. And then the x-intercept is where the graph crosses the x-axis, which is when y equals 0. So you are going to want to solve f of x equals 0. So these are the x and y-intercepts. For instance, if we look at y equals x squared minus 1, the y-intercept is going to be where it crosses the y-axis. That's x equals 0. So we get y equals minus 1. The x-intercepts are where it crosses the x-axis, so we have to solve y equals 0. So x squared minus 1 equals 0. So x squared equals 1, x equals plus or minus 1. Okay, so far we have the domain and we have the intercepts. What else can we look for? Okay, another thing is maybe symmetry. So there are different types of symmetry we can look for. One is when the function is even. So if f of minus x equals f of x for every x in the domain, then we say the graph is even. So what does that mean? So f of minus x equals f of x, that's saying the graph is the same for positive x and for negative x. So it's saying if we look at the graph for x bigger than 0 and the graph for x less than 0, it's going to be the same on either side. Or a nicer way of saying this is the graph is symmetric if we reflect in the y-axis. So if we manage to draw the graph for x bigger than 0, then we can fill in the graph for x less than 0 just by kind of doing a reflection and copying what was happening on the other side. Okay, then if f of minus x equals minus f of x for every x in the domain, so notice there's the extra minus sign there. So if we swap x to minus x, we don't get back what we had before, but we get the opposite sign of that. Then we say that f is odd. And how to think about this? It means that the graph is symmetric if we rotate 180 degrees around the origin. So we take the graph and say the right side, and then we spin around 180 degrees. That's going to give us the graph on the left side. Okay, and then finally, if there is a constant, so that f of x plus p equals f of x for every x, so here p is a constant. So if when we translate, we get back what we had before for something, then f is called periodic. And the smallest such p that we can take is the period. And okay, let's see some examples of these. So for instance, even functions will be x squared, absolute value x, cosine of x, right? If we replace x by minus x all squared is the same as x all squared. Absolute value of minus x is the same as absolute value of x. Cosine of minus x is the same as cosine of x. And if you think of the graph of any of these, right, the graph for x bigger than 0 is the same as the graph for x less than 0. Okay, what will be some odd functions? Well, for instance, x cubed and sine x, right? Minus x all cubed is the same as minus x cubed. Sine of minus x is minus sine x. So notice the extra minus sign that hangs around. If you think of the graph of these, if you spin the graphs around by 180 degrees, you get back to what you started. Okay, so these are odd functions. And then finally, typical periodic functions are sine x and cosine x, and those trig functions, they are 2 pi periodic. If I do sine of x plus 2 pi, I get back sine of x, right? If I have sine of pi over 2, that's the same as sine of 5 pi over 2, and so on. Okay, so that's symmetry. Next up, we have asymptotes, which we've seen pretty recently. Right, we said there are 2 types, there are horizontal and vertical asymptotes, and if the limit as x goes to infinity or minus infinity is L, then y equals L is called a horizontal asymptote, and it's going to be a horizontal line. And if as x approaches A, either the right-sided limit or the left-sided limit is plus infinity or minus infinity, then x equals A is a vertical asymptote, and that's a vertical line. And remember, it was important that the horizontal asymptotes were, and the vertical asymptotes, they're equations. So not just L, but y equals L because it's horizontal, or x equals A because it's vertical. For instance, we've seen many examples of these, but y equals e to the minus x. As x goes to plus infinity, y goes to 0, so there is a horizontal asymptote. As x goes to minus infinity, y goes to infinity, so there is no asymptote on the other side. And okay, tangent of x has vertical asymptotes at x equals pi over 2 and at x equals minus pi over 2. For instance, with pi over 2, if we look at what happens as x approaches pi over 2, say from the left, if tangent of x is sine x divided by cosine x, so sine of x, which is the top, is going to 1, and cosine x, the bottom, is going to 0 from the positive side. Okay, so that's going to go to plus infinity. Okay, next up, we've seen even more recently increasing, decreasing. So if f prime is positive on an interval, that means f is increasing. If f prime is negative, that means that f is decreasing. If we want to find the local max and the local min, there are 2 steps. So first, we're supposed to find the critical numbers, which are where the derivative is 0 or does not exist. And then depending on what is easier, depending on if we know f prime or if we know f double prime, we can use 2 tests. So there is either the first or second derivative test. For the first derivative test, we look at one of these critical numbers and we look for a change in sign of f prime. So if f prime changes from plus to minus, so from positive to negative, that means that f changes from increasing to decreasing. So if you think of the picture, that means there is a local max. If f prime changes negative to positive, that means that f changes from decreasing to increasing, so there is a local min. Okay, next up, you don't have to use both tests, but you can use either the first or second derivative test. So if you have the second derivative handy, you can look at the sign of the second derivative at the critical number. So if the second derivative at c is less than 0, then there is a local max. If the second derivative at c is bigger than 0, then there is a local min. Okay, so this was basically the first order behavior, meaning the behavior that the derivative tells us. Okay, so next up we have the second order behavior, which is the behavior that the second derivative tells us. So that's concavity, right? So if the graph, by definition, we said the graph is concave up if it lies above its tangent lines. But an easier way to find this, or if we only have formulas to hand, was to look at the second derivative. This is when the second derivative is positive. Okay, alternately, we said the graph is concave down if it lies below its tangent lines, meaning the second derivative is negative. And there is an inflection point if we change in concavity. Okay, so just to kind of summarize, how would we use all these properties? So there are quite a lot of properties we're looking for. How would we use them to sketch? So maybe the easiest way to do it is to look at what are the key points where something is happening and then try to fill in the intervals in between. Okay, so think of what's happening in the long-term behavior. So draw the asymptotes. So that's what's happening as x goes to infinity or as x goes to minus infinity, or what's happening as y goes to infinity or y goes to minus infinity, right? So that's the large scale, far away from the origin behavior. That's telling you where the graph is going to end up as you zoom out. Okay, and then we have to plot the important points where something interesting happens, which are where it intercepts the axes, where there's a local max or a local min, where there are inflection points. So keep in mind the local max and min are where it's changing from increasing to decreasing or vice versa. The inflection points are where it's changing from concave up to concave down. So these are all the points where we're either meeting an axis or where something interesting is happening. And then we have to fill it in between, right? So in between all of the interesting points, we have to decide whether it's increasing or decreasing, or whether it's concave up or concave down, and so on. Okay, and then finally, if there is some kind of symmetry, then we can, instead of sketching the graph for the whole, the whole x-axis or whatever, or for everywhere in the domain, if there is symmetry, we can sketch it on a smaller piece and then use the symmetry to fill it in. For instance, if we were sketching sine of x, it would make sense only to think about 0 to 2 pi and then just fill in the rest by translation. Okay, so here let's see an example. So here is x squared divided by square root of x plus 1. Let's try to compute everything and try to sketch the graph. And to save us some time, I'm going to have computed a lot of this stuff earlier. Otherwise, it would be really boring. So let's think, what is the domain? So the domain, what do we need? We need everything in the formula to make sense. So the numerator is x squared, which makes sense for all x. And the denominator is the square root of x plus 1. So since there is a square root, we need the inside to be positive. So we need x plus 1 bigger than 0, or bigger than or equal to 0. So we need x bigger than or equal to 1, or bigger than or equal to minus 1, rather. And since then we are dividing by a square root of x plus 1, we need to make sure we're not dividing by 0. So we need to make sure x is not equal to minus 1. Okay, so just to say that again, we need to make sure that we're taking the square root of something positive. So x has to be bigger than or equal to minus 1. And then we can't divide by 0. So in fact, x has to be strictly bigger than minus 1. Okay, then we look for the intercept. So the x-intercept is going to be when y equals 0. And that only happens when the numerator is 0, so when x squared equals 0 or x equals 0. And the y-intercept is the y value when x equals 0, which is y equals 0. Okay, so actually this curve intercepts both of the axes at 0, 0, and there are no other intercepts. Okay, what about symmetry? Okay, so if we try to do f of minus x, then the top is going to remain unchanged. But if we plug in minus x in place of x, the bottom becomes very different. And there's no way to simplify it so that we have just f of x or f of minus x. So it's not even or odd. And of course, there are no sines, cosines, there are no reasons that it should be periodic, so this is not periodic either. So there's no symmetry, unfortunately. Okay, what about asymptotes? So remember, horizontal asymptotes are what happens as x goes to infinity or as x goes to minus infinity. But here, the degree of the top is 2, and the degree of the bottom is x to the 1/2. So as x goes to infinity or as x goes to whatever, okay, x can't go to minus infinity because it wouldn't be defined, but as x goes to infinity, y is going to go to infinity. Okay, in vertical asymptotes, we're looking at what we should plug in order to make y go to infinity or minus infinity. Okay, so we're looking for when the bottom is 0 in this case. So here that would happen when x plus 1 equals 0 or x equals minus 1. Okay, when is it increasing or decreasing? So to find that, we should look at the derivative. So if you use the quotient rule and you simplify, we can get this formula. So remember, if we're trying to figure out the sign of f prime, we should look at the sign of each of the individual factors and then try to put it together. So when could the sign change? The sign could change when each of these individual factors is 0. So in particular, it could change at x equals 0. It could change when 3x plus 4 equals 0, which would be x equals minus 4/3. But remember, the domain is only minus 1 to infinity, and minus 4/3 is not in the domain. So actually, that doesn't give us a place where the sign can change inside the domain. And then how about the bottom? Okay, the bottom is 0 when x equals minus 1. Okay, but again, minus 1 is not in the domain, so that doesn't give us a place where the sign can change. So as long as we stay inside the domain of f, which we have to, the sign of f prime can only change at x equals 0. Okay, so we have to check on either side of x equals 0. Okay, so we check x bigger than 0 and x less than 0. If x is bigger than 0, then all the factors are positive. So f prime is positive, so we're going to be increasing. If x is less than 0, but remember we still have to be bigger than minus 1 to stay in the domain, then the x is going to be negative. The 3x plus 4 will be positive. The bottom will be positive. We have one negative, so that's going to be negative. So f prime is going to be less than 0. It's going to be decreasing. Okay, and then we look at the local max and local min. So we said at 0, the first derivative is 0, and it changes from being decreasing to increasing. So if we change from decreasing to increasing, that means there is a local min at x equals 0. Okay, next up the concavity and the second order behavior. So if you use the quotient rule and you differentiate and you simplify, we can get this formula. So we have to look for when the second derivative can change in sign. So that happens when the second derivative could be 0 or when the bottom could be 0. But in this case, the numerator is a quadratic. So we're trying to figure out when this quadratic will be 0. And there's no nice factorization, so we have to look at the quadratic formula. And if you look at the quadratic formula and you check, b squared minus 4ac, here, if you do b squared minus 4ac, the discriminant is negative. So because we're not taking square roots of negative numbers, there are actually no solutions that make the top equal to 0. So the top is never equal to 0. And for instance, we see that when x equals 0, it's 8, which is positive. So it's never equal to 0, and it's positive at one place. So in particular, the top always has to be positive. Okay, so the numerator here is always positive. Similarly, the denominator, since x is bigger than minus 1, the denominator is always positive. So actually, f double prime is always positive. Okay, so f double prime is always positive. F is concave up on the domain minus 1 to infinity. And okay, since it's always concave up, the concavity doesn't change, so there are no inflection points. Okay, so this is everything we talked about very briefly for this one example. So let's try to see what this looks like on a picture. So keep in mind, we want to start with the interesting points where something is happening. So we want to start with the asymptotes, and the intercepts, and where it changes from, where there are local max and local min, and where the concavity changes. And then we want to fill in on the subintervals in between when something interesting is happening. Okay, so here it is. So we said as there are asymptotes at x equals minus 1, and we said as x goes to minus 1 from the right, the function goes to infinity. So we're going to have to start somewhere up here. And then we said as x goes to infinity, there isn't an asymptote, but x goes to plus infinity. So we're going to have to end somewhere on the top right. Okay, and then in between, there was this interesting point, which is which is actually everything. So at 0, 0, it intercepts both the axes, so it intercepts the origin. And this was also a local min. So here is the local min and the intercept. There are no other local min or max, no other intercepts. So these were the interesting points, right? The asymptote, the long-term behavior, 0, 0, which is the intercept and the local max min. And then we have to fill in what's happening on the subintervals, which is from -1 to 0 and from 0 to infinity. So what's happening in between. So we have to make sure we choose the right concavity and the right increasing or decreasing. So if we look at what's happening from -1 to 0, we said from -1 to 0, the graph is decreasing, but it's always concave up. So we're going to need something that's decreasing, but less and less steeply because it's supposed to be concave up. Okay, here is something that's decreasing and concave up. And then looking next from 0 to infinity, or x bigger than 0, we have to choose to make the right choice. Is it increasing or decreasing? Is it concave up or down? Okay, here it's increasing and concave up. So it will look something like this. Okay, so here was a pretty simple example, but you can see the main steps. You fill in the long-term behavior, put in the asymptotes, label all the points where something interesting is happening, and then on each of the little subintervals that you have left, it should be increasing or decreasing, and that will be the same on that subinterval. And it should be concave up or concave down, and that will be the same on that subinterval. So you just have to fill in the right kind of shape. Okay, and we'll do many more examples of these in person, or at least on this live session. Okay, and the last thing to talk about are slant asymptotes. So we had horizontal asymptotes, we had vertical asymptotes. What are slant asymptotes? So horizontal asymptotes are where it approaches a horizontal line. Vertical asymptotes are where the graph approaches a vertical line. Slant asymptotes are just where the graph approaches a diagonal line. Okay. So how do we detect that? So a diagonal line has the form y equals mx plus b for some constants m and b. So if we look at the difference between f of x and mx plus b, so we're looking at the difference between the equation of the curve and the equation of the line. If we look at the difference and that goes to 0 as x goes to infinity or as x goes to minus infinity, so if that difference goes to 0, then we say the line y equals mx plus b is a slant asymptote. And okay, here I didn't want to write both, but there is nothing special about x goes to infinity. So we could approach something else as x goes to minus infinity, and that would also be a slant asymptote. So they could be 0 or 1 or 2 of these asymptotes. Okay, and here is just a general picture, right? There is a line, and the curve gets closer and closer to the line, either as x goes to infinity or as x goes to minus infinity. Okay, so let's see an example of this. So I'd be quite surprised if this came up on a test, but let's just make sure, just to be on the safe side. So when do these happen? Okay, they can happen for all different types of functions, but one kind of interesting example is rational functions where the degree of the top is 1 bigger than the degree of the bottom. And in that case, we can find the slant asymptotes by division. So for instance, here is a function x cubed divided by x squared plus 1. Let's try to find any slant asymptotes. So we should use long division to rewrite this. So if we use long division, we can rewrite this function as x minus x divided by x squared plus 1. And now there is clearly a degree 1 piece, and then there is a piece x over x squared plus 1 that's going to go to 0 as x goes to plus or minus infinity. Okay, so we suspect, if we siphon off this constant or degree 1 part and keep the rest, we suspect that we should choose y equals x as our slant asymptote and keep the other part as the remainder. So if we look at the difference f of x minus x, that's minus x divided by x squared plus 1. Now that right side goes to 0 as x goes to plus or minus infinity. Right, so we had to take away the x. If we just started with our formula f of x, it wouldn't go to 0 as x goes to plus or minus infinity. But once we take away that x, it does. So y equals x in this case is our slant asymptote. Okay, so that's about it for summary of curve sketching. So we are just using everything that we've seen so far. We put it together in a sequence of steps to sketch the curve or try to understand the curve. And basically the idea is look at what are the key points where something interesting is happening. So look at the asymptotes, look at the intercepts, look at the local max and min, look at where the concavity is changing. And then on each of the subintervals that were left between those points, we can try to fill in according to whether the graph is increasing or decreasing, concave up and concave down. So sketching is kind of intimidating, but if you break it down into the little pieces, the advantage of looking at these subintervals is that on each of those subintervals, nothing is really changing. It's just the same behavior. So we just do it piece by piece. Then hopefully we can break it down and manage to do it. Okay, we'll do more examples on these in a live session. Thanks, everyone. Take care.